Have you ever thought about what an unbreakable code really is? Well, today we're diving into something pretty mind-bending. How a totally new kind of computer, a quantum computer, could solve problems that are literally impossible for even the most powerful supercomputers we have today. We're going to explore the strange and wonderful quantum rules that give them this almost unbelievable power.
And it all starts with a number. Now, we can't show all 617 digits here, but this is the kind of massive number that protects everything from your online banking to your private messages. The entire security system, things like RSA encryption, it all rests on one simple but incredibly hard challenge: finding its two prime factors. That's the key that unlocks the whole thing.
For a normal, classical supercomputer, this is basically an impossible task. We're talking about thousands of processors running for millions of years, and you'd still need longer than the age of the universe to find the answer. For today's computers, this code is, for all practical purposes, unbreakable.
But get this, a future large-scale quantum computer could potentially crack the exact same problem in about 8 hours. So, how? How is that even possible? What is this different kind of tool doing that a supercomputer just can't?
Okay, so this incredible speed, it comes from a completely radical shift in how information is stored and processed. The first key idea is something called quantum parallelism, and it all starts with the most basic unit of information itself.
So the computer you're using right now, it runs on classical bits. You can think of them like tiny light switches. They can only be on or off, a 1 or a 0. A quantum bit, what we call a qubit, is totally different. It can exist in a state of superposition, which means it's both a 1 and a 0 at the exact same time, right up until the moment you look at it. And that weird ability unlocks a level of parallelism that is just, well, it's mind-boggling. Just 100 of these qubits can represent and explore over a non-jillion possibilities all at once. That's a 1 with 30 zeros after it. It's not just a faster computer. It's like having a nearly infinite number of computers all working on the problem simultaneously. But here's the catch, and it's a big one. This massive parallelism is kind of useless on its own. See, if you have every possible answer existing at once in this superposition and you just measure it, quantum mechanics says you'll just get one single random result. It's like having a library with every book ever written, but you're only allowed to pull one out with your eyes closed. You need a way to find the right one. So to solve that problem, we need a second, even stranger quantum trick. It's a mysterious connection called entanglement. And if superposition gives us the library of all possible answers, entanglement is how we find the right book.
Entanglement is this wild state where you can link two or more qubits so their fates become inseparable. They just stop acting like individual things and start behaving as a single coordinated system. If you measure the state of one qubit, you instantly influence the state of the others, no matter how far apart they are.
One of our sources provides a perfect analogy for this from the children's story, Swimmy. In this story, a school of little fish learns to swim together in the shape of one giant fish to scare away predators. Well, entangled qubits are just like that. They're many tiny parts working in perfect coordination as one powerful, unified system.
This teamwork is created using tools we call quantum logic gates. A really important one is the CNOT, or controlled NOT gate. Just think of it like a simple if-then command. It links two qubits, a control qubit and a target qubit. And the rule is simple. If the control qubit is a 1, then you flip the state of the target qubit. That's it. That simple conditional rule is what forges that inseparable entangled link between them.
Okay, so now we have our two quantum tools: superposition to explore every possibility, and entanglement to make them work as a team. So how do we actually combine them to crack that 617-digit number? Well, the answer lies in finding a hidden pattern. The absolute genius of the quantum solution, which is called Shor's algorithm, is that it doesn't even try to guess the factors one by one like a normal computer. No, instead it transforms the factoring problem into a totally different one, finding a hidden repeating pattern, a period, within a special mathematical function. Turns out, if you can find that hidden rhythm, the factors can be calculated pretty easily.
And you know, when you see a diagram for Shor's algorithm like this one, it looks incredibly complex. But don't worry about all the details. What's really important to know is that every single piece of this complicated-looking map has just one goal: find that hidden period.
So here's how the quantum computer actually pulls this off. First, superposition creates this massive quantum state that represents all the possible answers. at once. Then, and this is the crucial part, using gates like the CNOT we just talked about, the qubits are entangled. This step allows all those countless possibilities to interact and interfere with each other, kind of like waves rippling across a pond.
And this interference is the absolute key. A final step, called the quantum Fourier transform, acts like a lens, focusing all of this quantum interference. It cleverly orchestrates all these waves so that the wrong answers cancel each other out, while the waves for the right answer, that hidden period we're looking for, all add up and amplify each other. So when you finally measure the qubits, the right answer is basically shouting the loudest. And it's the entanglement that makes this coordinated chorus possible in the first place.
This powerful method really shows that breaking codes is just the beginning. This fundamental ability, using superposition and entanglement to find hidden patterns in overwhelmingly complex systems, can be applied to some of the most difficult challenges we face. We're talking about things like precisely simulating molecules to discover new medicines, designing revolutionary new materials from the atom up, or solving these huge, complex optimization problems for things like financial modeling and global logistics that are they're completely out of reach for today's computers. As one of our sources so eloquently puts it, this technology is both a sword and a shield. The sword is its power to break the very cryptographic shields that protect our entire digital world.
But the shield is its potential to help us solve challenges in medicine, climate science, and materials research that, right now, we can only dream of. A whole new era of computation is dawning, and it really leaves us with a profound question. How are we going to choose to wield this incredible power?